just thick. It is viscous enough to taste. It hits you a quarter-mile out. A wall of pungent, stinging vapor that waters the eyes and sears the throat. This is no kitchen. This is a high-security intake sector in the heart of California's Central Valley. And sitting before us is a literal mountain of biological volatility. 40,000 pounds of raw allium sativum, garlic. And that is just the morning delivery. In the next about 24 hours, this monolithic sterile processing facility must ingest, process, and completely transmute 1 million pounds of this raw material. That is the weight of a fully loaded Boeing 747 composed entirely of sticky, sulfurous, irregular organic bulbs. But this mountain is ticking. From the moment the garlic leaves the earth, a biological countdown begins. The bulbs are 65% water and loaded with sugars. Left in the sun, they rot. Handled roughly, they bruise them, and they oxidize, turning brown. In the world of industrial food science, brown powder is worthless. The goal is white gold, a silky, pristine powder that flows like liquid and retains the chemical potency of the fresh bulb. The engineering paradox is severe. Garlic is nature's superglue. When crushed, it becomes a paste that cements moving parts together, clogging gears, jamming belts, and gumming up sensors. Turning the stickiest vegetable on Earth into a dry, free-flowing powder without destroying the machinery requires a violent, invisible war against moisture, fought with aerodynamics, centrifugal force, and laser ballistics. The harvest trucks back into the intake hoppers now. We spend zero time in the fields. The romance of agriculture dies at the loading dock. What happens next is pure industrial warfare. Raw bulbs dump onto the intake conveyance system with a rhythmic, deep bass thud that vibrates the concrete floor. The journey from dirt to dust begins now. The clock is ticking. The first stage of transformation is arguably the most delicate. We need to dehydrate the garlic, but drying a whole bulb is impossible. Moisture trapped in the center would never escape before the outer layers burned. We must dismantle the bulb into individual cloves. In a home kitchen, you would smash the bulb with the flat of a knife. Here, such blunt force would be catastrophic. Crushing the bulb breaks cell walls, releasing alliinase enzymes that immediately degrade flavor and darken color. We need to disassemble the structure without bruising the meat inside. The solution is a deceptively simple machine that looks like a conveyor, but operates on the principle of differential shear force. Garlic bulbs enter a narrow compression zone, sandwiched between two monolithic rubber belts, one on the floor, one on the ceiling. The trick is velocity. The top belt moves slower than the bottom belt. As the bulb is gripped by the rubber, this difference creates a tectonic shearing effect, the mechanical equivalent of rubbing your hands together but applied with hydraulic pressure. The bulb is rolled and twisted simultaneously. Torque snaps the structural integrity of the root plate, the hardwood base holding the cloves together, and shatters the papery outer skin, but leaves the delicate clove inside perfectly intact. The gap tolerance here is surgical. The distance between the belts is calibrated to within 80 thousandths of an inch. If the gap is too wide, bulbs roll through whole, clogging downstream peelers. If too narrow, the machine becomes a juicer, crushing garlic into a mash that costs the facility $10,000 an hour in lost yield. Technicians monitor belt tension in real time. You can hear the machine working, a rhythmic, rubbery squeak, snap, as thousands of bulbs are effectively dislocated every minute. The output is a chaotic mix of loose cloves, shattered root plates, and flying paper skin. The cloves are exposed, but still wearing their jackets. That tight, sticky inner skin that clings to the meat like a wetsuit. Removing that skin without water is the next impossible hurdle. We are now deep inside the facility. The air is drier here, and the noise level jumps to a deafening roar. This is the domain of the Venturi air peeler. traditional canning factories peel vegetables using steam or caustic hot water baths. That is strictly forbidden here. To make dry powder, adding water is counterproductive. Worse, wet garlic at room temperature is a petri dish for bacteria and mold. This entire line must remain bone dry. To peel 1,000,000 sticky cloves without a drop of water or a single touch, we use a controlled aerodynamic explosion. The cloves feed into a customized pneumatic chamber, a hurricane in a shoebox, relying on the Venturi effect. As garlic falls through the chamber, nozzles blast compressed air at a staggering 120 psi into the vortex. To understand the violence inside, imagine standing in a wind tunnel where the wind changes direction 20 times a second. Air pressure fluctuates so radically and instantly that the skin literally fails to hold on. It expands and contracts faster than the clove inside, popping off like a button on a tight shirt. Through reinforced observation glass, individual cloves are invisible in the white blizzard, a chaotic storm of flying papery chaff and naked cloves tumbling in freefall. The sound is aggressive, a rapid fire, hiss, pop, like a steam locomotive depressurizing. This is the sound of air doing the work of 1,000 human hands. Physics gives us a secondary advantage here. Skin is lighter than the clove. As the mixture exits the pressure chamber, it enters an aspiration column, a vertical wind tunnel. Massive industrial fans suck the air upwards. The heavy, naked cloves fall against the wind, landing safely on the inspection belt, while light, papery skins are caught in the updraft and vacuumed away into extraction ducts. The separation is brutal, but effective. We have stripped the garlic naked, using nothing but the atmosphere itself. However, the chaos of the harvest brings intruders. Stones, clumps of dirt, and pieces of wood often survive the initial cleaning. If a rock enters the slicing machines, it becomes a projectile. We need a filter faster than the human eye. The conveyor belt moves at a blurring speed, carrying a waterfall of peeled cloves. To the naked eye, it is a continuous white stream, but hidden in that stream are imposters. White rocks, bits of glass, or cloves that are rotten and discolored. A human technician might catch one defect every few seconds. The Tomra 5B optical sorter catches thousands every minute. This machine is a marvel of modern robotics, combining high-definition cameras, laser spectroscopy, and pneumatic ballistics. As garlic cloves launch off the end of the conveyor belt, they enter freefall for a fraction of a second. In that split second, they are scanned by lasers from both front and rear. The processor analyzes the light spectrum of every single object, looking not just for color, but for chemical composition. It knows a stone reflects light differently than a garlic clove, even if both are white. It spots the subtle beige of a rotten spot or the telltale refraction of clear plastic. When the computer identifies a target, it doesn't stop the belt or use a mechanical arm. It uses a sniper shot of air. A bank of high-speed air valves positioned just below the camera line calculates the trajectory and fires a localized bullet of air, a force push, that hits only the defective object in midair. The accuracy is terrifying. In slow motion, a stream of good garlic falls in a perfect parabolic arc into the accept bin. But every few milliseconds, a stone or bad clove is kicked out of formation by an invisible punch, flying into the reject chute. The sound is a rapid-fire staccato. Thud, thud, thud-u-t. It sounds like a silenced pistol firing 20 times a second. This digital sniper fire ensures that what lands on the next conveyor is 99.9% pure organic material. But now we face the geometry problem. A whole clove of garlic is too thick to dry. If we put these cloves into the oven now, the outside would turn to charcoal while the inside boiled. To create a powder, we must first create a flake. We have reached the most dangerous machine on the floor, the Urschel Model CC. From the outside, it looks like a modest stainless steel drum. Inside, it is a centrifuge of death. This machine must slice thousands of pounds of irregular slippery cloves into uniform wafers, exactly 60 thousandths of an inch thick. If the slice is too thick, it won't dry. If too thin, it burns. The challenge is that garlic is not a carrot. You can't just push it through a grid. It is odd-shaped and tumbles unpredictably. The solution is G-force. The interior of the slicer features a massive impeller, spinning at 3,600 revolutions per minute. Cloves drop into the center of the spinning vortex. Instantly, centrifugal force grabs them and pins them against the outer wall of the drum. This is the gravitron effect. The garlic is no longer tumbling. It is frozen in place by the sheer velocity of the spin, pressed flat against the stainless steel ring. Stationary razor blades are mounted into the wall of the drum. The garlic isn't chopped by a moving knife. The garlic is the moving projectile. It is forced to slide across the stationary blades at 60 miles per hour. The result is not a chop. It is a shave. The machine produces millions of perfect, paper-thin cross-sections in seconds. The physics here are critical. By using centrifugal force, the garlic is sliced cleanly without being crushed. We need the cell structure to remain open to release moisture, but we don't want to squeeze out the essential oils. The audio signature of this zone is a high-pitched turbine whine that rises as the load increases. It is the sound of kinetic energy. The floor vibrates under your boots. Out of the bottom flows a blizzard of wet garlic flakes. They look like snow, but the smell is overpowering. We have maximized the surface area. The garlic is now vulnerable. It is wet, exposed, and beginning to react with the oxygen in the room. We must stabilize it immediately. We must enter the artificial desert. This is the largest machine in the facility. The Buhler Aeroglide conveyor dryer is a monolithic structure, 100 feet long and 2 stories high. It is essentially a terraforming engine. We are about to take these wet slices, which are 65% water, and bring them down to 6% moisture. But we cannot just blast them with a flamethrower. High heat destroys the volatile sulfur compounds that give garlic its flavor. If you cook it too hot, sugars caramelize, and you get toasted garlic, a different product entirely. We want raw white powder. The process involves vertical cross-flow aerodynamics. The dryer is divided into 4 distinct climate zones. The conveyor belt carrying the garlic is perforated steel. Zone 1 is the shock zone. Here, the air temperature is a blistering 210 degrees Fahrenheit. Huge industrial blowers force this hot air up through the bed of garlic. This initial blast is designed to kill surface bacteria and flash evaporate surface water. It creates a crust on the slice, blocking the shape in place so it doesn't shrivel into a hard rock. As the belt moves into zone 2 and 3, the temperature drops, but the airflow reverses. The wind now blows down through the garlic mat. This is the curing phase. The goal is to gently coax moisture out of the center of the slice without burning the edges. It is a process of mass transfer, pulling water molecules out of the cell structure and carrying them away in the exhaust stream. Thermal imaging cameras monitor bed depth and temperature. On the screen, you can see the heat map shift from a deep angry red at the entrance to a cool, stable blue at the exit. The sensory shift in this room is intense. Standing near the inspection doors, you are hit by a wall of dry, hot air. It feels like opening an oven door in the middle of the Sahara. The roar of the blowers is a constant, low-frequency rumble that rattles your chest. By the time the garlic reaches Zone 4, the cooling zone, it has been transformed. It entered as a wet, sticky vegetable. It exits as a brittle, bone-dry chip. You can snap it in your fingers. It is now shelf-stable. Biology has been paused, but a chip is not a powder. The customer, massive food conglomerates, making spice blends, sauces, and frozen meals, needs a specific particle size. They need Silky. To get there, we have to destroy the structure one last time. The dried chips are vacuum transported to the milling room. This is a contained environment, sealed off from the rest of the plant to prevent dust explosions. Garlic dust, like flour or coal dust, is highly flammable when suspended in the air. The room is grounded, and the equipment is explosion-proof. The hero of this stage is the Fitzmill hammer mill. While the slicer used razor blades for precision, the mill uses blunt force trauma. Inside the grinding chamber, a rotor spins at 3,000 RPM. Attached to this rotor are hardened steel hammers, rectangular blocks of metal that swing freely. There are no knives here. The machine doesn't cut the garlic, it obliterates it. Dried chips feed into the top and fall into the mosh pit. Hammers impact the chips mid-air, smashing them against the corrugated steel liner of the chamber. The garlic shatters like glass. Particles are trapped in this violent cycle until they are small enough to pass through a sizing screen at the bottom. This screen determines the mesh, the fineness of the powder. For today's run, we are using an 80 mesh screen. That means the holes are microscopic, finer than a grain of sand. The garlic particles bounce around the chamber, being hit again and again until they are terrified enough to shrink and escape through the holes. The sound is a grinding, metallic scream overlaid with the whoosh of the pneumatic suction system. From the bottom of the mill, the powder is instantly sucked away into a cyclone separator, which spins the air out and lets the dust settle gently into the packaging line. This is the moment of truth. What was once a sticky bulb is now a cloud of white smoke. The packaging line is a sterile environment of stainless steel and silence, a sharp contrast to the violence of the milling room. Here, the final product is flowing. It pours into the filling station like liquid silk. It is stark white, cool to the touch, and unbelievably potent. A single teaspoon of this powder contains the flavor intensity of an entire head of fresh garlic. QA specialists pull samples every 15 minutes, measuring moisture content, color purity, sewing, and particle size. If the powder is too coarse, it won't dissolve in a sauce. If too brown, it looks dirty on a potato chip. Today's batch is perfect, a bright, snowy white. But there is one final twist to this engineering marvel. Remember those millions of skins we blew off in stage 3? The mountains of papery chaff? They weren't thrown away. In a loop of perfect industrial sustainability, skins are collected, compressed into biomass fuel pellets, and burned in the facility's boiler room. The heat generated by burning the skins helps warm the air for the dryer. The garlic plant is, quite literally, powered by garlic. In the last 24 hours, we have taken a mountain of perishables, fought a war against rock and gravity, and won. We didn't fight the sticky nature of the garlic. We outran it. By peeling with air, slicing with G-force, and drying with aerodynamics, we have frozen nature in time. The result is sealed in moisture-proof bags, ready to be shipped to kitchens around the globe. It is the invisible backbone of modern flavor, engineered to perfection.